different aspects of a process using different data structures. And one part of the data structures are used to manage the memory, virtual memory that you might have found earlier a little bit. Apart from that, I'll talk about different system calls to be used for creation of a process, synchronization of a process, and termination of a process. So we'll talk about the different system calls, then scheduling of a process. What is the scheduling algorithm that is used generally in operating systems, in Linux-based operating systems or Unix-based systems? We'll talk about signal handling. It's a mechanism through which a process can communicate with some other process which is currently active in the system. We'll talk about the threads, multi-threaded systems we are all aware of. So what is a thread? How can we create process threads? And how can we manage them? How the threads can communicate? We'll talk about deadlock handling. And one of the most important topic is data access synchronization primitives or synchronization primitives. We'll consider here semaphores and monitors both, and we'll also talk about shared memory. Okay, how we create a piece of memory in the RAM that will be shared by multiple processes, so that they can coordinate or they can communicate through that shared piece of space. And also we'll talk about some of the basic inter-process communication mechanisms. So this is the entire set of topics that comes under the process management module. In today's particular lecture, I'll be talking about very brief about the Unix or Linux history that will be required, because throughout this course, I'll be talking about some system calls. I'll be talking about some commands which will be specific to Unix type systems, or the systems or operating systems which are developed based on the Unix philosophy. And Linux is one such operating system, which is a recent, the most recently developed one, and that is based on the principle of free and open source. So I'll just talk about very briefly about the history, and then I'll mainly focus on discussing about some basic shell commands through which we can monitor or observe the different parameters or features of a process which is running, so that we can have a feel of the processes. And then finally we'll try to define the process, and that will be then. So the overall idea of this today's lecture will be to have a feel of the processes through the basic commands, the shell commands, and we can see that how processes are created, how they can communicate, and all this, just to have a feel of it. And we'll end up with the process definition. So this just one slide on the history. I'm just trying to summarize the whole story. So what it shows in the top will have the Unix was developed long back. I mean, it was in late 60s, and the first OS that was developed, Unix-based OS was developed. It uses PDP-7 assembly language, so that was purely written in assembly language. But then people thought that it is not possible to write the whole OS using assembly level language, and because of that, once the C language was developed sometime in the early 70s by Ritchie, Dennis Ritchie and all. So then Ken Thompson, who is also a colleague of them in AT&T Bell Labs, he took the initiative to write the entire Unix operating system in C, and with some bit of assembly code within it. And then in 76, AT&T Bell Labs released the version 6 of the Unix system, which was widely used in many in the industries and also in the academics. And then people started trying to, once the code is there, so they try to use the code, not only use but also modify and add new features to it. So as you can see, there are several verticals while developing the Unix systems. In the extreme end, you will find the Xenix, which was licensed by where the Microsoft got the license of selling it or giving it to the customers. And then later on, sometime during the early 80s, it was they just handed over to SCO Corporation. and they started a different business. So, but during that period, it was Microsoft was the highest commercial, like the companies who sold the license of Linux. At the same time, the Bell Labs, AT&T Bell Labs, they keep on changing new versions and all. And version 8, so this version 7 was kind of the ancestors of all the Linux, the Unix implementations that came later on. And as you can see that this system 3, that was the first commercially marketed Unix by Bell Labs. And these square boxes are some landmark versions which got released. And as you can see in the extreme right, there is another column of development, which was basically led by University of California, Berkeley, uh, through the Berkeley Software Division. And that is better known as BSD Unix. So they also took the same philosophy and they modified it in their own way, and they got different versions. And this 4.3 or 4.4 BSD was more or less very stable and became very popular, and mostly in the academic environments. So all the academic installations, they mostly preferred BSD Unix. But in the industry or commercial use, as you can see that system uh, version 3 or this version 8, and these are all in use. And then in system version release 4, that was a kind of the first effort where industry and academics together just they concentrated in coming up with a commercial release which can be used extensively, as well as new research or new additions can also be done. So this was a very stable and a very popular version of Unix. And then Solaris also, Sun Microsystems, then IBM, they all joined hands. They had their own implementations, but all these Unix was basically took the idea of the philosophy from this system V6 or V7 that was originally developed by AT&T Bell Labs. And we can see that from this BSD, it triggered the Mac OS, which was actually the project was started by CMU, and in CMU in 1985. And that later on, one of the persons from that group joined Apple, and Apple actually implemented that, modified that in its own. And here comes the Linux, which was, so this whole story was till late 80s, and in the early 90s, right in 91, the Linux came, and it was a different story. It was inspired from the developments here, but it was developed from completely a different angle, because in 1984, the GNU project started by Richard Stallman, and he also founded this Free Software Foundation to raise funds for this GNU project. And under the GNU project, he developed tools like GNU Compiler, GNU Debugger, and Emacs in 1980. And when this Torvalds developed Linux in 1991, he basically took, because these are open source and free to use softwares, so basically took a lot of utilities from this, and he wrote the kernel, and that came up in 91. He released the first Linux in the internet, and it was again following the same philosophy, let it be open source and free. So he, there are a lot of contributions from that point onwards, and almost like 30 years uh, it got evolved. There are many distributions came. So the point that I want to make is, in this course, whatever system calls, whatever commands I use, I basically use for demonstration. I'll use Ubuntu, and that's a Linux distribution. But when I talk about the system calls, the internals of the system calls, some of the system calls like fork, wait, and signal. So those details of the system calls, I'll refer to the book by Maurice Buck, which was written in late 80s. So that was based on this BSD or system version 3 or 4. So, but as you can see, the same logic holds, because the same philosophy, the same internal algorithms were implemented by the Linux developers also. So there is always a match, and these days you can run any application that runs in Linux that also will run in other implementations of Linux and Unix. So they are more or less system-wise, they are exactly the same, the feature-wise. But internally, when you think of the data structures, there might be some differences. Even the scheduling algorithms also more or less are the same. Okay, so our focus will be on Linux, but at times we'll refer to Unix, the traditional Unix systems, and some of the books written on that. So before we get into the details, we often use the keyword kernel. So kernel means the low-level core of the operating system. So as you can guess, the operating system, the core of the operating system deals with memory management, the file management, CPU management, or the processor management, that process management that we are right now talking about. But apart from that, so that is not enough. So to run that, you need a nice user interface. Sometimes you need some UI tools. Sometimes you need some compiler so that the programmer can write applications on top of it. So the kernel is just including all the core modules of the operating system, and the term kernel is mainly meaningful in terms of Linux or Unix. But when you talk in terms of Windows, that also has a core, and which is better known as executive. In batch OS, it was better known as monitor, like this. And the generic term in many books, you will find it as supervisor. Okay, so we'll stick to the term kernel because we'll be referring to Unix or Linux type OS. So before we get into the examples or see the basic commands, shell commands, let us know the basics of it. So the initial processes. So when you boot the system, Linux or Unix system, when it boots, so the very first process that creates, so it's not that all of a sudden all the processes are created. So you need to create the very first process. So the very first process that gets created is so the first kernel process, it is created and it has got the PID I0. So what is PID? So in the system, which is a multi-programming operating system, and Linux or Unix that we are talking about is typically an example of time-shared multi-programming OS with networking features. Okay, so if you recall the classes of operating systems that we talked long back, so this is of that type, time-shared multi-programming with networking features. And because it is multi-programming, multiple processes will be running simultaneously. So to distinguish between these processes, the system came up with a unique ID assigned to each process. So this ID is called a process ID. It is something similar to the IDs given to the roll numbers or like the registration numbers given to the students when they get enrolled in for a particular course. So these IDs should be unique, and in this case, these are all unsigned integers, and it has got a maximum limit also. Okay, so we call it as PID, the process ID. And on the 32-bit machines, the maximum limit is generally 32768, which is system defined, and you can find these values in this particular subdirectory. Okay, in this file. And a 64-bit machines, it is typically 2 to the power 22, approximately supporting the presence of 4 million processes at a time. And that is typically it's a huge lot of processes that you can create simultaneously. Because when a new process starts, the idea is if the system has already created 20 processes, so if a new process comes up, maybe it is a kernel process, maybe it is a user process, it will take the process ID 21. Okay, so the OS maintains these numbers, and the last unused ID will be assigned to the new process. And if it gets exhausted because of this limit, because if you try to think of like I call for, we'll see what for does. If I keep creating processes from a program, I write a program which just keeps on creating a new process infinitely, definitely this value will be exhausted at some point of time. And then what happens? Then the numbers restarts, and maybe there will be some limit also in terms of the memory of the resources that we use. So the thing is, if this number gets exhausted after repeated creation of the processes, so it will then wrap around. So that is how it is done. So what we mean to say is every process in the system will have a unique PID, the process ID, and the first process that gets created after the booting, it's a kernel process, it's a system process, and we do not see it, we do not need to see it also. Okay, so that process is the kind of it takes the responsibility to start some other kernel processes. Okay, so it creates several other kernel processes, and uh, and it also creates the very first user process, which is called the init process. Okay, so this is called the init process, and its PID is 1. So the init, it has got a typical name. We'll see that in a short file. So this is the first user process. So the user, through the shell, it can see the presence of that process, and this process is basically the kind of parent of all the other processes that you create, all the other user processes that you create in the system. Okay, so if we run a process, so we'll see that how it happens. So the init is basically the grandparent of all other processes. Grandparent in the sense, so everything. So these in the root, and all other descends from that, and all other processes are directly started by init, or the processes will be started by some processes which has been started by init. So in some sense, there's a kind of hierarchy that gets created. We'll see that hierarchy, process hierarchy. Okay, so in that process hierarchy, this is the process 1, and then some other process, say maybe it is say 4, and then that process creates some other process, say 7, like that. And maybe by the time the init creates some other process, say 9. So in that way, there's a kind of process hierarchy, and you can see that the init process becomes a parent, not only the parent but the grandparent of all processes. Okay, and interestingly, if some process like and because of this, that any process in a system need to be created by some existing process in Linux or Unix. And as you can see, excepting this kernel process, the first kernel process PID 0, every process has got its parent, right? So from that idea, so we can say that one will be the parent process, one will be the child process. So there is always a parent-child hierarchy. And interestingly enough, if say, so in this case, 4 is the parent of 7 and 7 is the child of 4. So if this parent process, immediate parent of any process dies or terminates because of some reasons, okay, so then you cannot have a process without any parent. That is a typical. So it's like in a real life scenario also. So if the parent dies, then somebody will take the responsibility. So in this case, this init process becomes or takes the responsibility of the parent. Okay. So in case this parent dies, this process becomes orphan. So then this init process with PID 1, the first user process, will take charge of this process. And so in that sense, the processes, the user processes in the system will always have a child process, parent-child hierarchy, and that keeps maintained. And in fact, a process can know, it can, I mean, through some system calls or commands, you can get to know your parent processes ID. You can get to know your own process ID also. Okay, so this is possible. And the system need to keep track of all these through some data structures. So let's get back to the story. So first PID 0 gets created, the first kernel process, which creates the first user process, the PID 1, which is called init. And then init in turn creates the terminal process. So terminal means, say, when the system is running as a user, say for example, you don't have a GUI. So even in GUI also, you may be interested to open a terminal. So through the terminal only, we know that we can, so that when a terminal is created, so this terminal is a software terminal. So when a software terminal is created, so in that terminal, what is running is a shell process. And what is a shell? A shell is a interactive command line interpreter. So the idea is, if there's a, so we'll see it shortly. So if we consider the init process, so init process, its task is to spawn the or to create the terminal process. Say sometimes it is called as getty. So getty means it is trying to create the terminal. So if a user initiates a login, and if it is a valid login, then the terminal process is created. And at the same time, the terminal process in turn executes a shell process. Okay. And in Unix or Linux, there are multiple shell options. So what is a shell? Shell is an interactive command line interpreter. So the basic idea is, in the shell, in that dollar prompt or in that hash prompt, so whenever you type some commands for the OS to run, so the shell takes those commands, parses it. If it is correct, it will ask the OS to run it on your behalf and will produce the results in that terminal. So that is what it does. But it can do many things beyond that. So it can run intelligent scripts. Scripts means you can have logic added to it, and you can write a script with multiple commands used in a different form. So so the shells are not only just are able to interpret small single commands, but it can interpret maybe complex scripts also that can do multiple things simultaneously. So in Linux, the default shell is bash. So bash stands for GNU Born Again Shell. So why this born again means born shell? As you can see here, this was developed and written much earlier during those mid 80s, and this was a because throughout the Unix development, users actually interacted with the operating system through some shell, and initially there were no GUI based interface. It was purely shell or terminal based interface. So in those days, such kind of shells are really useful. So Bourne shell is one very well-written shell and popular shell, Corn shell, C shell, and all this. So this Bourne shell is actually it has been rewritten during the development of Linux. Linux actually prefers this to have it as a default shell, but you can always switch to other shells. You can download it like that. So now some shell commands. So when you run a terminal, and if you come up with this, so this means this is a command line, as you can see, and this is a shell that is running. So if I write pwd means present working directory, it will be prompted like this. So the present working directory, right from the home, it will show the entire path. If you write ls-l, that means this is listing the contents of the files and subdirectories of the same under the same directory, under the current working directory. Okay, and this -l means this is long listing, so it will be showing all the details of it. So it has got right now, as you can see, the snapshot was taken. It has got one file, it has got the one executable file, and it has got a subdirectory also. So the sizes and the time when they created the users and their permissions, like whether you can run it, and D stands for it's a directory or subdirectory, and this is executable, that's why this is X here. Okay, and this is simply a text, so that's why these X's are not there. So these things you can decode. Many of you know these basic commands also. And if we write cat this hello, it will show the contents of that file. Definitely we can always use an editor like Emacs or some other editor, Sublime editor, but you can see the contents. Now let us come to a very important command which will be required for process monitoring. So this is PS, and PS command stands for, it's a short form of process status. So what is process status? So this displays the currently running processes, displays the different parameters of the current running processes. So we'll see it, I'll show it in Ubuntu, but let us see that how it works and what are the parameters exactly it is showing. So if I write simply PS and press enter, so it might show information of only two processes. I mean, those are the two processes which was running during that time. So it is a command means that, so this table lists the significance of these different fields as it is shown. Okay, so if you write here PS-E, that means E stands for select every processes. So what you see here, so this TTY1, it is associated with the terminal, so the terminal window that you have opened. So if you open two terminal window, then the second terminal may be identified as TTY2, like that. Okay, so there is one terminal, and within that terminal, the bash, it is the bash is also it's a shell process, so it's a process which is running. It's running the bash shell, and this PS is a command. Whenever you run that command, it becomes a process. So these are the two processes, and these are the PIDs of those processes which has been assigned by the system. It's 180 and 197. So bash started early, and then later on PS started. So it has got a higher number. The TTI, the time when they created, like this. But if you type PS -e, then you would get it selects each and every process in the system. So in addition to bash and ps, you find here the presence of init, which we are talking uh, uh, just a few minutes back. So init is the process and whose PID is just 1. Okay, so this is the process which got created just after booting, and it got created by the first kernel process which has the PID 0. Okay, so its PID is 1 and it is not associated with a particular terminal. That's why it's question mark. Okay, so this is not associated with the terminal. It's just a kind of process which is running, and this is a user process. And you might ask that there are so many kernel processes and why they are not shown. So these lists all the user processes that you are running, or maybe it is running in the system. Okay, it will not show the kernel processes. So this init, so this init corresponds to the that get ty. So it's a kind of terminal process you can think of. Okay, so these are the few processes. Now if you type ps-f, then f means it chooses the full format. Full format means, as you can see, there are many other things which is shown here, and interestingly it shows the parent process ID also. As you can see, the bash and ps both, they are having the parent this terminal process, this 179. Okay, sorry, the bash, it has got the parent as 179, and the ps, it has got the parent as 180, because when you run the ps, it is executed by the shell process. So the shell process has initiated it, so it becomes a parent process. Okay, so but if I type ps-ef, so it will not only show all the processes, it will show the full format, so everything is there. And here you can see there is a clear hierarchy that appears. So the init process with PID 1, it has got 0 as its parent. So 0, and then comes 1. First kernel process and the first user process. And then under this as a parent, it has initiated the terminal process, which is 179. Okay, and as you can guess, by the time several other system processes they have been created, and they are doing all the memory management and all other several other process management tasks. And then under the 179, which is the terminal process, the bash shell process got created, which has got ID 180. And under this bash, when you are in that shell process, from the shell you executed ps, the command which actually triggered another process corresponding to it, and that has got 200. And as you can see, the timing, so they are started, I mean, the snapshot when I took, it was the timing shown. So in that, so these are clearly, there is a hierarchy of processes that got created. Okay, and these are the fields, the significance of the fields. S time is the start time. This time is the number of the amount of time that it uses the CPU, and all this is a command. And this is a user ID. User means it's a root user, and I have, when I run this shell, I run it as in the user mode, Subhrata as a user. Okay. So the PS can be used in other form also. As you can see, this EF, this is an option which is supported by the POSIX standard. Okay, so it is supported by the POSIX standard, and there is always a kind of clash, or might be the conflict of interest, because BSD and AT&T, you can imagine those two vertical columns of development. So they always had a fight of like who will be taking the lead. And because of that, in some Unix variants which follows the BSD, they prefer to use provide these options AUX. So they don't have a option to write -ERF like that. But Linux, being inherited from both of these two ancestors, it accommodates. In Linux you can run both of it. So you can write PS AUX, or you can write PS EF. Both will work. In fact, if I run PS AUX, you will find that this is output. So it is indeed in a long format, and it includes this X stands for, it will include even the background processes. We'll explain in within a short while what this means. Just hold on, and then this means all the processes. This is equivalent to that E. This A is equivalent to the E option, and this use adds a column for controlling for the controlling user of each process. So this was already there in that case. So what we can find here, what is missing, you can see what is missing is this PPID, the parent process ID. You cannot display in this format. I mean in this option. So that is not there. So if you want to get the parent process ID information, you should write in that -EF format. But it gives you a few more very interesting parameters. One is the CPU percentage, one is the memory percentage, one is the virtual memory. You see, VSZ is virtual memory usage. This one, RSS, you see, this is a resident set size. It is related to primary memory, but the details we will know when you know the details of virtual memory management. So these two are related to the virtual memory management or the memory related parameters. This is the memory, means the physical memory that you are consuming, how much, and these are actual CPU time that you are consuming. And strangely, they are all zero in the sense they are almost it's very negligible. That's why it is zero. And we'll show some examples where these are significant. We'll see that in today's class. Okay. So the point is, this init is not associated with TTY that we found. This init, which is a basically terminal process, this is basically inherited from this one. Then bash and pxaux. Okay, and this the start time, this is fine. And there is one more interesting field. It is status. So what is the status? This gives you the status of the process which is running or which is active. So there can be a process can be in different status, in different state. In the next class, we'll talk about the different possible states of a process and the events then that can trigger such jumps. So for the time being, you can look into this particular table, which gives the all possible status codes, right? So here, if you find that SSL, so S capital stands for sleeping. So this init process is sleeping. It is not actively running in the system. So it is nothing to do now. It has spawned all the required processes, and there is no other task scheduled for it. Small s is if it is this process is a session leader. So init is a session leader. So that was SS, and this L stands for processes multi-threaded. So we are not going to details of multi-threading. Later on, we'll see what it means. And here, this PSAUX, you can see it is in the running mode. So when you just ran it, it was in the running mode. That's why it is R. So R stands for running. Strictly speaking, runnable. So this may be running or it is ready to run. So whenever it gets scheduled, it will run like that. So this PSAUX is more informative, excepting that it is not having information of the parent process ID. Otherwise, you see it has got so much of information regarding the memory, and this is, you see, the virtual memory space of this is this much, and the real memory kind of thing. You can see there is a huge difference. The virtual, so that what we tried to explain in my introductory classes. So the process actually is so much big, and the amount of memory CPU, I mean RAM, that is utilizing is only this much, and still it is running, and you don't feel the difference that it is not currently completely loaded in the RAM. Okay. So from this PS command, I think you get a feel of the processes that are already created, or some commands which create some process through the execution of the command. So how they can be visualized and how the parameters can be tested. Now, instead of one shell, if I create or instead of one software terminal, if I create 2-3 terminals, we can do that. So each terminal will run then one shell, maybe the bash shell. So in this case, if we run 3 terminals, and if we from one particular terminal, if I type PSAUX, then what do we expect? So it will show all the possible user processes in the system from any terminals that you like. So as you can see here now, so after running this in a sequence, I run it in the last terminal. So what I found is there's a bash which corresponds to this this terminal running in this terminal. This bash corresponds to the shell running in the second terminal, and this bash corresponds to the process shell process running in the current terminal, this one. So you see that. So if you have not done anything, so these are the two init system-wide init process, but there are 3 shell processes running, and each of them is coming with a terminal process, init/init and bash, like that. Okay. So this is extremely powerful command through which we can really test our processes. We can see the progress, and we can find out different interesting facts. So now, before going to the remaining slides, I would like to show you the. So this is one. You see, so I'm using Ubuntu Canonical, and here so here if I write pwd, the present working directory is this. Then I check ls. I found that there is a subdirectory. I switch to that subdirectory, and I then type ls. Is the screen visible? Hello?
Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
Okay, fine. So now you see I switch to the code, and within the code I get to enter into this subdirectory. Oops. So here if I write ls, so these are some of the programs I already wrote, and those are all pretty simple ones, just to see that if I type a program, if I run the process, then how it looks like. And here I try to create some processes which intentionally I would expect them to use some bit more of CPU as well as memory, which was completely missing in the prior examples, right? So here, if I, without doing anything, if I write here ps -ef, what do we expect? So here we have not executed any other user processes except the ps command. We should have the init, the basic init, then the init, that's the terminal process, and the shell. So these are the cases. So you see that, and there are 2 bash because we have already created, I have already opened 2 shells, 2 terminals, that's why. Okay. So this is what I'm getting, and you see this ps has been executed at right at this moment, 1516, and this terminal, this new terminal that I created only just now. Now the previous terminal was created long back. Okay, so this terminal process as well as the shell process was created long back, and this is the new one that I'm creating. Okay, so the time is given, and you can see here the parent process ID also. Okay, and you can think of the hierarchy of the processes that gets created. Okay, so but still the time is 0. But all of them, so these 2 are associated with terminal 1, and these 3 are associated with terminal 2. Okay, so each terminal that you create will be having some identifier TTY1, TTY2, TTY3 like this. And but both the terminals I have logged using my login with my login name. So now, so this part is fine. So now if I would like to check this one, so like GCC, I would like to write this dynamic, okay, infinite loop. So what is the infinite loop code? Let's see this. So cat so this is just very simple. It just runs an infinite loop. That's all. So let me compile this. CC. And I write infinite loop. So let's see, we have this infinite loop. So this is a executable corresponding to this source code. So if I would like to run this, what I do? slash. Okay. So I run it. What do I see? So simply the prompt goes off because you are running a code which is not displaying anything. You can't see anything, and it's an infinite loop. So it never stops. It keeps running. So if I want to run ps command here, it's not possible. Simply not possible, right? So then how to do that? So we can take help of the other terminal now, and just let us see that if I have successfully executed it. So can you see this? So this is the infinite loop process. So this is the user process, the user application process, you can say, which is running and which has got the process ID 333 prior to the execution of PS. So this is 333 and this is 344, and this 333 it has been run from the bash shell. So this is from 265. So this 265 is the parent of this, and this PS it has run from the previous shell, that is 245, all that it shows, right? So you can see, but the thing is what to do here. So you cannot really so the only way to stop it is Control C, and then it stops. And once it stops, if you type it here, you see it's not there. So this process you have terminated by pressing Control C. So this process is off now. So the process, if it is running, you can really see it, and if it is all by a moment, you cannot see it. So now you can see, and then the things are like this. You see the values that it shows. It is not showing too much of it because the memory and CPU is not there. So let us run it once again, and then try to see the PS AUX. What do I expect? I may not see the parent, which I have already checked earlier. It will be the bash shell through which it has been executed. But I would like to see the memory usage, CPU usage, and the primary memory, virtual memory, and all this. And here it is. You see, it's not doing any IO. It's basically executing the for loop. It's an infinite for loop and keep on executing that like that. So that's why the CPU usage is 83%, almost keeping busy. But it cannot make it 100% because you'll see later the scheduling will not allow you to keep using the CPU for long. I mean, you cannot monopolize. Even though nobody is interested, everybody is sleeping. You see, all the rest of the processes are sleeping. So this init is sleeping, so everybody else is sleeping, but still you cannot, if you want, you cannot utilize the CPU. So that's something stops you to monopolize and ensures that it is in the spirit of true interactive environment, right? So that's why it is hard to get something with 100% CPU if you just run one process, no matter. So it's purely a CPU intensive job. Okay, but the memory usage is almost zero because we have not created any memory, even local memory, I mean local variable and all this. And the virtual say space, it is so that is also not just few bytes, because even though you don't use, you will have a stack, you will have some space in different segments. So there are 4 segments, and even though you don't use it, there will be some default value they should come out, but they will be all blank. So that's why this virtual memory, virtual space of even this very simple program, it is having some significant conjugations in significant space. But the resident set size, that the something related to the primary memory usage, it is too small because we are not actually using any memory. Okay, so this is this is a pre-allocated space. So whenever the process starts, some frames are pre-allocated for them because the OS never knows that when you are going to use it. So all these policies you'll see later on in memory management. Okay, so this is there, and if I write it here, it's still running. Okay, so if it is running, I know how to stop it from here. If I press Ctrl C, I can stop it. Do you know any other way to stop this?
Sir, to use the kill command.
Which one? Which command?
Kill.
Yes. So if I try kill, so kill means what? It's literally it's killing something. but it has got other purpose. So kill is not meant for killing processes. We'll see it later on while talking about signals. Kill is basically trying to send a signal, but its name is something quite ambiguous, as we'll see it later. But so if I write kill, so whom I want to kill? I want to kill this 336 with PID. So write 336 and see what happens. Now it got stopped. Okay, but why don't we see the termination that it aborted the message here in this particular screen? Why we don't see it? But we see it here. Why? Because that particular process, this particular executable process, user process, is associated with terminal 2 and you are in terminal 1. Okay, so anything that comes that appears related to the that particular process will always, so this is associated with this terminal, so anything that happens will appear here but not here. But from this terminal you can always send a signal to that process. Got it? So who is sending the signal? This shell process. So the shell process running in this terminal is actually sending a signal to this process, and that actually terminated forcibly. So this is a kind of interaction. So one process, so these are all processes. Now here, maybe this process, this process actually triggered a signal. It actually sent a signal to, it actually send a signal to this process. Okay. So processes, when they are concurrently running in the system, they are coexisting in the system. So one process can send a signal to the other process, asking him to do something. It may not be just mere termination. It can be some other issues, some other tasks, and receiving the signal. The process which received the signal may do something else. We'll see that how to use it in a much more meaningful way. But these are examples which shows that using PS you can really feel what the processes are doing. If you write a CPU intensive process, you can see that the utilization is pretty high, and you can send, using some command, you can send signals also to that process. So it's basically sig int, so that signal is sent and that immediately terminates the process whenever it receives it. Okay, so this is what we found, and now let us try to run some other process. So this process, we found that memory is getting utilized, CPU is getting utilized to a large extent. So let us try something else. Say I would like to run this process, infinite dynamic allocation. So what is that? It is also a very simple one. What it does, so instead of just running infinitely, it does something very dangerous. Every time it asks for new space, some amount of, so it's like it's 10 KB space. So every time it asks for 10 KB space and keeps asking for it forever till the whole system gets exhausted. So something very extreme. So this means you will be utilizing memory. So this memory is required because it will be allocated from the heap segment, and heap has got some limit. You cannot, so your heap cannot eat up the entire system space. So heap has got some limit. So it will definitely run for a number of times, I mean for a long time, but it cannot run forever. That's for sure. Okay. So if I compile this code, so GCC finite. So now I compile it and I name it as infinite alloc. And I see that this is the executable corresponding to this particular code program. So now if I run it here, what you do? Okay, so before I do that, I can I just touch upon one point. If I consider the previous case, so like infinite loop. So if I want to run infinite loop, now the thing is, I know that infinite loop, if I run it, it will be you will not be able to see the prompt. The prompt goes off, because it is running and it runs forever. So can I make it run in the background and still I can have the access to this shell? How it is possible? So till now, whenever I run like this, the process is holding the terminal. Okay, it becomes a foreground process. If I want to run the process in the background, so that I want to make the shell process free for accepting commands, so what should I do? Hello, can you hear me?
Control Z.
Yes, sir.
So if I give ampersand, you see, so if I give this ampersand, now what happens? You see the process is running. Okay, so one process starts running, and this is the PID of the process that got created, but you got the shell also free. So now if you write here ps-aux, what do you find? Now this is free. You can still type commands, but this infinite loop or this process now becomes a background process. So background in the sense it releases the shell for other use and it runs in the background. Is that fine? And these background processes are sometimes known as daemon processes. Okay. So these daemon processes, if it's a process like this, I do something else and something else, like I do ls and I do pwd and all this. At some point of time, I find that okay, this is still running, and I want to kill it. So now, because the shell is now free from the same terminal, I don't have to reopen another terminal. From the same terminal itself, I can pass on a kill command, noting probably that I have done some mistake and I have run executable, which will never stop. So I just look into the PID of that 356 and I kill it. And because this process is associated with the same terminal, this will appear here itself. It's terminated. Okay, and if you run here this, it goes off. You got the point? So the thing is, in some cases we may not be interested in running the process in the foreground because it might take too much of time, and I want to, by the time I would like to make my terminal or the shell free for other usage. But if you do that, and if the process it has got some printf statements or cout statements, then it's a problem. Then even though you are doing something, it will keep popping up those displays, and that we probably may not want. Okay, so a background process is not expected generally to interact with the user. So if it is a CPU intensive work, or if it is a non-interactive process, then you can run it in the background, and in that way, from the same terminal itself, you can initiate multiple processes like this. So you can write this, then you can do this. What I'm doing. So now I've got one executable, but I am running 3 instances of that executable. And if I run here this one, what I find, there are 3 executables or 3 processes, or you can say 3 instances of that same executable. What is executable? This is a command, infinite loop. So this is executable. It has got just 1 instance saved in that, but that creates 3 running instances, and each of them spawned as a new process. So as you can see, the code is the same, the binary executable is the same, but when you run it, it manifests in 3 ways. Okay, it is something like a particular student, he enrolls in BTech, and he also or he enrolls in a PhD say program, and maybe he is willing to do parallelly some master's program also, like he enrolls in both of them. So physically the same person, so it's like this, but he is enrolled into different programs, and he manifests 2 of its existence as an enrolled student. So are you getting the point? So a particular program may be associated with multiple processes, so it's one to many association. Is that fine? And here in the status you can see that all are in the running mode. Okay, so they are running, and you can see that this is 73%, 73%. So they are trying to utilize the CPU in the best possible way. So now let us kill all of them. So it's 361, 62, 63. So everything got cleaned up, and we have this much. So now we are interested to run that process, that infinite loop, infinite dynamic allow, right? But here again, the point is I would like to run it as a background process because I know what background process is. So just give an ampersand at the end. It will make it background, and but still it is associated with the same terminal. So still you can see the prompts in that same, but you are free to use. So let us run it in a background. So it came up with a, as you can see, so although you have released these PIDs, you see 363, 62, 63, 61, but it is taking which one? The next available free. So it will wrap up only if it gets completely exhausted. So if you keep running and keep running, you can write an infinite loop which creates forks multiple processes and see that when it wraps up. So here it uses 366, even though knowing that the 361, 62 is available because those processes are terminated. So those numbers are, those roll numbers you can see. It's like if somebody leaves, if some student is not in roll, probably you are not going to assign that not in roll number to some new incoming student. So the same policies are taken in the academic section also. Okay. So now once it is running, if I write here AUX, now find that this is working. Now something serious is happening here. CPU percentage is fine because it's almost same as that of the previous code, but now it is consuming a huge lot of memory. It's 81%. And now can you see? Now see the fact. So this virtual space is increasing in size. It keep increasing in size. You see, it was this. After a short while, it is this. Now it is blowing up. So it basically growing faster in exponential because you are eating up every time you are requesting for space from the heap. And at the same time, the frames, as it is required more and more, the resident size is getting increased, and the CPU and the process management, the memory management dynamically adapts to it. We'll see that how it is possible. So if you don't require, you will give a small space, but if you find that you are really hungry and you are